Hi, I'm Cliff Liu. Today I will talk about our paper, Connected Components on a PRAM in Log Diameter Time. This is joint work with Robert Tarjan from Princeton and Peilin Zhong from Columbia. First of all, I will talk about the computational models. There are two theoretical models that capture the essence of parallel computation very well. The first one is called Massively Parallel Computation Model, or MPC for short. In this model, the input is distributed in many machines or processors, where each processor holds a polynomial fraction of the input, say n to the delta, where delta is a constant. The computation proceeds in rounds. In each round, the processor can do unbounded local computation, but can only send or receive at most n to the delta words to and from other processors. This is because in real world, the communication is usually the bottleneck. Therefore, our goal here is to minimize the number of communication runs. Many modern computational platforms such as Hadoop and Spark can be abstracted as an MPC model. Another more classical model is the famous parallel random access machines, that is, the PRAM model. In the PRAM model, there is unlimited shared memory, and each processor can only hold a constant number of words. In each round, each processor can read or write a cell in the shared memory in constant time. Our goal is to minimize the time, processor number, and the work, where the work is just the total primitive computations over all processors during the execution. In the family of PRAM, there are many variants. The weakest one is called exclusive read, exclusive write PRAM, the EREW PRAM, where concurrent read or write on the same cell at the same time is not allowed. If we allow concurrent read, the model becomes CREW PRAM. If additionally we allow concurrent write, but when multiple writes to the same cell at the same time, an arbitrary one wins, but we don't care about which. Then this model is called arbitrary CRCW PRAM, and this will be the main model we considered in this paper. A stronger model is the priority CRCW PRAM, where each processor has a distinct priority, and when multiple processors write the same cell at the same time, the processor with the highest priority wins the write. In most cases, the MPC model is more powerful than a PRAM. For example, computing the OR function on the CREW PRAM requires log n time. If you want to compute the prefix sum of a length n array or sort n elements, you need at least log n over log n time, even on a stronger priority CRCW PRAM with any polynomial number of processors. This is by Beamer and Hastad. These two functions are often used as primitives for other more complicated functions and algorithms. However, prefix sum and sorting can actually be solved on an MPC in O1 over delta time, which is a constant. In general, any PRAM algorithm can usually be simulated on an MPC with asymptotically the same running time. Therefore, it is widely believed that the MPC model admits faster algorithms than that on the PRAM model. In this talk, we will be focusing on a fundamental graph problem, that is, to compute the connected components on the undirected graph with n vertices and m edges. Initially, each edge only knows about its two endpoints. For the output, each vertex needs to know a unique vertex in its component as a representative, so that when we want to determine whether two vertices are in the same component, we simply just compare their representatives. The history of connectivity in parallel computing can trace back to 50 years ago. The first log n time algorithm is given by Slovak and Wyshkin in 1982, using linear number of processors on an arbitrary CRCW PRAM. Their algorithm is deterministic and was later simplified by our version Slovak. If we want to use fewer processors, one can actually with Ko and Wishkin's log n time algorithm, that is almost linear work, only with the inverse Achmed factor overhead. If randomization is allowed, Gazit has log n time linear work algorithm, which is also on the arbitrary CRCW PRAM. This line of research culminates in the work of Harper and Zwick. Their randomized algorithm can run on the EREW PRAM in log n time and linear work. All these algorithms are very complicated. Recently, Liu and Tarjan have an extremely simple log n time algorithm, and it is deterministic. Many graphs in real world actually have a small diameter. Motivated by this, the first breakthrough for small diameter graphs comes from Andoni et al. In Fox 18. Their MPC algorithm runs in log d times log n time using linear space. Later in Fox 19, Benajad et al. Improved this time bound to log d plus log n. However, whether such kind of time bound can be obtained on any PRAM is unknown before this work. In our paper, we give an arbitrary CRCW PRAM algorithm that matches the time bound of the MPC algorithms. Note that when the graph is slightly denser, the algorithm runs in exactly log diameter time with high probability. In fact, obtaining a PRAM algorithm out of the existing MPC algorithms are not easy. Let's go back to the previous slide. The lower bound of computing the OR function on a CREW implies that the same lower bound for connectivity. More importantly, the log n of log n lower bounds for prefix sum and sorting and other functions hold under the very strong priority CRCW PRAM, even with polynomial number of processors. Both Andoni et al. And Benajad et al. The algorithms use prefix sum and sorting extensively, since the running time is 1 over delta, which is considered as a constant on the MPC. However, if you run a direct simulation of their algorithms on a PRAM, their algorithm would suffer a log n over log n slowdown in the running time, which gives no improvement over the log n barrier. In the rest of the talk, I will first give some high-level ideas of the algorithm. Let's consider an arbitrary path in the graph. If each vertex contracts to the leader vertex with distance at least 2, then the graph contracts to one vertex in log d runs, where a leader is just a vertex in the current graph fixed by some global loop. For example, you can just sample each vertex as a leader independently with some probability. This is like the repeated squaring the adjacency matrix, like this. That's where the log d comes from. However, this naive approach is not practical, as it might require n square space per vertex, since the degree can be as large as n, especially after contraction. So the key idea in Fox 18 paper is that if every vertex has degree at least b, which is m over n initially, as we have m space in total, then sampling each vertex as a leader independently with probability roughly log n over b gives that each vertex has a leader neighbor with high probability. And the number of vertices after contraction reduces to roughly n over b. Then in the next round, each vertex would have space roughly b squared. Observe that the degree lower bound increases double exponentially over the rounds. Therefore, the number of outer loops is log n. For the inner loop, increasing the vertex degree is done by expanding the neighbor set like the repeated matrix squarely, but is truncated to fit the space per vertex which is log d inner loop running time. Pushing this idea even further, in the Fox 19th paper, instead of increasing the degree of each vertex uniformly to at least b in each round, they allow vertices to have different space budgets. More specifically, they define the vertex levels. Initially, all vertices are at level 0, and the level increases over rounds. A vertex at level k means it has a budget space of m over n to the 2 to the k. So the maximum level can be at most log n. The algorithm maintains the following key property. Each vertex v either increases its level, or the vertices at distance 2 on the path decrease their distance from v to 1. So this is the first case that the level increases. The second case is adding an edge to decrease the distances. Together with the property that the skipped vertex has a minimal level among its neighbors on the path, we can use a potential-based argument to prove a log d plus log n running time bound. The high-level idea is actually simple. Either we would have something like running a repeated matrix squaring like this, or we would reach the maximum level log n. But the detailed proof is kind of complicated, since there are many subtle issues. You can read the updated archive version of their paper, or our SPAA paper if interested. In the PRAM model, things are a bit different. Guided by the same high-level idea, there are many challenges. First of all, vertices at level k has a budget space of m over n to the 2 to the k, but how do we assign space or processors to it at the end of each round? We first use a simple randomized algorithm to reduce the number of vertices to n over polylog n. Then we can call the approximate compaction algorithm by Goodrich, which maps the distinguished elements in a length n array to a compacted array such that all distinguished elements are approximately indexed. Goodrich compaction algorithm runs in constant time if each element owns polylog n processors. That is why we first reduce the number of vertices to n over polylog n. A more difficult challenge is to maintain that if a vertex v doesn't increase its level, then all vertices within distance 2 must connect to v. In the MPC algorithms, they use sorting and the prefix sum to achieve this, which is not feasible on a PRAM due to the lower bound log n over log n. Our key idea is hashing. Each vertex v owns a hash table. Firstly, all neighbors hash themselves to this neighbor. Then hash the vertices in the hash tables of the vertices in the hash table of v into the new hash table of v. If there is a collision when doing the above hashing, we just increase the level of v. Note that we might lose some vertices in the hash table due to a collision, but we cover this case by level increase. Hashing also naturally removes duplicated neighbors, which is highly non-trivial in their MPC algorithms. We very carefully choose the size of the hash table such that the level of v remains the same with good probability, because we don't want to increase its budget space easily. As a result, we can prove the total number of processors is OM with good probability, which is what we want. After log d plus log n round, any path contracts to at most 2 vertices, which implies that the diameter of the new graph is 1. We can actually check this because you need to determine whether the algorithm terminates in this phase by doing another round of hashing to see whether any hash table changes in this hashing or there is a collision. At this point, we only need a PRAM algorithm that computes the connected components of the graph with the diameter 1 in desirable time. We borrow the idea from Andoni et al. To finish the algorithm. In our case, each vertex obtains enough neighbors in constant time, instead of log diameter time in Andoni et al.'s algorithm, because our current graph is just a collection of clicks. Using the same leader contraction framework, the vertex budget increases double exponentially, which means the loop terminates in log-log-n runs. Again, the detailed implementation uses hashing extensively, but I cannot go into their details during this talk. Our PRAM algorithm should also be favorable in practice due to the simplicity, and more importantly, the hashing technique should be much faster than doing prefix down and sorting frequently. The formal results are the following. There is an arbitrary CRCW PRAM algorithm that computes the connected components in log D plus log based m over n time with probability 1 minus 1 over poly m log n over n. Additionally, we also give an arbitrary CRCW PRAM algorithm that computes the spanning forest in log D times log n time with the same success probability. Spanning forest is slightly harder as it is a set of spanning trees of the components. You need to compute all these spanning trees. When m is like n to the 1 plus omega 1, both of these two algorithms run in log D time with high probability, which are optimal under the two-cycle conjunction. There are still some open problems. For example, can we remove the log-n factor? Is it possible to obtain a log D plus log n time bound for spanning forest and other graph problems on a PRAM or MPC? Also, the log n lower bound for connectivity in the CREW PRAM assumes worst-case instance. Can we get better bounds for small diameter graphs on weaker PRAMs? Thanks. This is the end of the talk. Thank you very much.